In this video, we are going to talk about how we can actually probe silicon, so the transistors and pins inside of the chip. And I'm super excited to hear how this can be done. And John is going to explain this. So first, my question will be why we would like to do these kind of things?
Yeah. So if we go back a bit, when I was in college, I was taking kind of some, let's call it like VLSI type class. And I asked, like, what is a transistor? And, when I looked at the textbook and I talked to the professor, I didn't feel like I got like enough of a meaty answer where I was like, okay, but really, what is a transistor? Like, how do you actually make a transistor? So I started, decapping chips and taking them apart until I actually saw a transistor and I said, aha, that's what a real transistor looks like. It's not quite what's in the textbook, but kind of sorta. And I just love that process of just kind of learning about, what's in the world and kind of, making sense of it.
So that's how you actually started probing inside of the chips.
That's right. Yeah. And so kind of followed up on that was, I did a lot of and still do, a lot of kind of reverse engineering for compatibility. So, it's like, hey, I have some old piece of hardware that I want to keep working. The software doesn't work anymore with it, or it's broken or something. And I started, for example, with this big laser system that I wanted to fix. And so I needed some information from it about, how to get it working in like repair mode, maintenance mode. And so I started getting into the embedded security side of things, learning about like, hey, you can't get the firmware out of this chip. But actually you can if you know what you're doing. And so I started looking at like, okay, well, how do you, use UV to reset the security system of this chip or put needles in there? What's the architecture of the chip that the manufacturer didn't tell you about? And that's what got me into this really deep stuff of really, really going into that lower levels of the chip. And, over time that, got more and more advanced. I started with much simpler things. And, as I got more experience and, kind of grew the operations, graduated more to like micro probing and more advanced instruments.
So how do you do it? Like, do you put there like teeny tiny needles, or how is it done?
How is it done? Well, we have some pictures for that.
Okay.
We could skip ahead to some pictures of actual probes if that's a good starting point.
I would like to see the picture, but then I would like to go back to why we would like to do it.
Sure.
So you explain we would like to do it, for example, for debugging, or
Yeah.
for maybe even for production. They may need to do this, no? Checking the silicon if it's working. Then maybe if you would like to reverse engineering something.
Yeah. Document for compatibility.
Okay, so that's the nice word. I didn't know that.
Yeah, that's a nice word. But I would say document for compatibility, support legacy operations. Yeah, something like
Yeah,
that.
it's not always doing something, because sometimes this kind of reverse engineering, it has this kind of bad meaning, but it doesn't have to be always
Yes.
bad meaning, because sometimes there are really some older systems which you still would
Yes.
like to keep running, and there is no other way how to do it, just some kind of reverse engineering, because there is no documentation and nothing.
That's right. Yeah. And a lot of what I deal with, essentially on a day-to-day business is, enterprises that, need to support a legacy system. And, there's really no information about it. And, even the manufacturer doesn't have any information anymore. And so and sometimes I talk to the OEM itself and they're like, we need to create some documentation that has been lost for this
Mm-hmm.
part. Yeah, so I should be really clear that, I think a lot of people think of this as kind of a nefarious thing,
Mm-hmm.
like hackers are getting into your system, but there are a lot of reasons where this is, even the manufacturer is doing it, because that's just what they need to keep their products moving.
Mm-hmm. So show the probes. I'm very curious.
Yeah, sure. So, let me go a bit, and I think I have. So there's a card. Well, so there's different types of probes. So let's start with this one. This is one type of probe.
Okay.
This is a wafer level probe. So This is like if you designed a wafer that you're like, we would like to test this before packaging and make sure that die is good because it's very expensive to take that die, cut it, put it into a package with metal and wires, and maybe you have to do another test cycle on that. So they want to weed that bad die out as early as possible in the process. So these needles go down onto the wafer. They're all made of tungsten, and we have kind of a close-up of them here if you want to see what they look like in a little more detail. They call these cantilever blade probes. And it's really hard to see, but the actual tip, can you see my mouse
Yes, I
cursor?
can
I
see.
hope. Okay, yeah. The actual tip is over here. I think you can see them a little bit easier
Yeah.
on these ones over here. And yeah, those are very precisely, positioned into that fixture, which I might add is especially on modern probe cards, is a very complex PCB, and getting these needles installed requires, special microscopes. And, these are really works of art when these are put together. I think you can see it a little bit here where, all these wires have been kind of hand soldered on there. So this is a very precise labor of love, I would say, to make these probe cards, because they're all bespoke and pretty low volume.
Do you know how big or how small are these needles?
In terms of like the tip of the needle
Yeah,
versus other properties.
or what is the pitch between them? So,
Oh, the pitch. I would say, it depends. Certainly for older chips, I would say a typical pitch would be like 100 micrometers. If that gives you a starting point. I think for newer chips, though, for various reasons, certainly could be a lot lower than that. Although I don't track that super close. But if that gives you like a starting point, and they also will stagger them. These are very linear, right? So there's much more crazy arrangements you can do, especially when you get into maybe like a memory chip or something like that. Where you're really pushing these really big data buses and have a lot of signal integrity constraints and stuff like that.
what is the lifetime of something like this? How reliable it is?
That's a good question. I do know that these needles do wear out, and they do also sometimes work, out of place. I don't have any specific numbers, but I do know that reworking these, is part of it.
Mm-hmm.
After so many probe operations, they may either tune the needles or fully remove them and replace them. Unfortunately, I don't have specific numbers there. I should also add for context that, most of my background is in microprobing and this kind of this failure analysis side. And only very recently have I started working on, I would call production level equipment, that's processing wafers and stuff like that.
Mm-hmm.
So I can say a little bit more about the prototyping side in
Okay, so
general.
how you do this? Because I don't think you have. Do you have
Yeah,
this kind of technology now?
I do actually,
Really?
but I don't use it. Yeah, there's one probe station behind me. There's another in the other room, but I've never probed a wafer here. Like it's just not part of my workflow, even though I technically have the equipment to do it. So,
Because maybe it's not
what
necessary. Because once you place the silicon inside of a package, maybe there are different ways how you can access or how do you, I don't know.
exactly, yeah. So the issue is, that once it's in the package, you really only need to access typically a few locations because most of the things like power ground are for any reasonable chip are going to be broken out to pins.
Mm-hmm.
So it's only adding a few select signals.
Mm-hmm.
Um, and let me see if there's a maybe a close up of these tips here. I think, yeah, kind of. You can kind of see here. So these are what the needles look like for this more prototyping equipment.
Mm-hmm.
Failure analysis level. It's a little bit hard to see from this, and unfortunately, I don't have a close up. Um, but the one on the right is basically
Can you
just a
move mouse
point.
with? I think
Oh,
I know where are the tips, but yeah, these are the okay.
yeah. So the tips are up here, and unfortunately, I don't have a close up of this, which would help a little bit. We can go to one of the other slides maybe where the needles are down. On these ones on the right, it's really just a sharp piece of tungsten um, wire. I think is the way I describe it, like almost like yeah, relatively thick. And if you look under a microscope, you'll just see, it tapers into a point. And these are used for bond pads. So, they're fairly meaty, relatively strong. The one on the left over here, you see this 10 versus 60. And unfortunately, off the top of my head, I don't remember exactly what that number corresponds to, but um, the one on the left though is kind of like 1 micrometer, point size or lower, if that gives you like an idea. And that one is what they call a cat whisker probe. So, it's hard to just, sharpen a piece of tungsten and get like an ultra fine tip. So for the one on the left, they take that tungsten rod and then they put the finest bit of wire you can imagine and kind of, I think it's like welded on, and that provides a very, very fine point, not for bond pads typically, but for actually probing a little small trace that's inside of an IC. Just like you debug a circuit board, you use that to get into that
So you
chip.
can probe directly on silicon.
That's right. Yeah. So we have an example, I think, on this first one over here. Let's, if we go back, you can see an example of what this can look like. And, this is large, process here. Um, so this is an old chip, which is great for practicing. And you see in this case, what we've done is we've put down two different needles. You see, just be really explicit, you see one
Mm-hmm.
here and one here.
Mm-hmm.
And we're checking out what's going on in this chip. And we're able to read signals on it. I hooked up an oscilloscope even on this particular chip, and it was no problem, was able to read the signals. And so, yeah, you can kind of get an idea of scale. Obviously, if you go to a more modern chip than this, you also need finer needles. You might need to do this in a SEM. You might need to use a fib to, reroute signals. So it's the same principle, but it just has some extra steps involved for the extra precision.
I have so many questions now. So the first one is,
Yeah,
uh, I know these chips, they are manufactured in many layers. So what if you
yeah.
need access something what is deeper? Because I don't know, is everything on the top? No.
No. So how about, yeah, so let's go through a little iteration, historical iteration. I think this may be a good excuse. So let's talk about like, so if you had something like this, so this is a bond pad, right? And you're like, okay, we need to probe here. In fact, you can see, I guess somebody had probed here previously. You see little
I,
marks here.
I would like to clarify. Bond pad is basically,
Oh,
it is on the silicon. It's the place where you would connect the wire, which will connect the pin from the chip, which is in the
yes,
package.
that's right. Yeah, with a wire bonder. Yeah,
Okay.
so little fine gold wires would attach here. Perfect. Thank you for that context. So this area right here, there's a cutout and the silicon dioxide that's, over the top of the chip. So you can electrically connect here just by, shoving a wire there. But if you were to try that over here, you'd have an insulating layer in the way. So, that's a bit of a problem. So the first problem you're going to run into is how to get through that. And what people did, in the very beginning, is you take one of the needles and you just kind of poke at that oxide until it kind of cracked and broke off. Or maybe you'd put some hydrofluoric acid, which you can etch through. But if you let it sit too long, it starts eating away your metal. And this is, neither of these are great. But if you're on a budget, they're going to work. So the next thing that people did was you get like a little small ultrasonic transducer that you put on the micro positioner, and then that does it more like
It's like
and that's a
drilling,
little. It's not drilling. It's almost like
breaking it.
poking it. Yeah, yeah, raking it. It's like raking it really quickly, because it's not twisting it; it's just shaking it
Mm-hmm.
violently, and it's like slightly more precise than you going, yourself, but really not too far off from that. So the first big like real solution was they have these like typically YAG lasers, so like these high power pulse lasers where you do like a laser strike on the chip. And I find this very satisfying to use, by the way. If I just need to like decompress a little bit, it's like Wrath of God on the chips, just like boom, gone. And and you can see like some test shots over here at various levels of power. And the idea is you basically blast off a layer of the metal by like ionizing and making it explode, and just enough where you make it explode off the oxide, but not so much that you actually rip through it. And so like you can see this pulse up here was too powerful. We actually destroyed the aluminum or whatnot. This one's perfect. We've knocked off just a little bit of the layer and we can probe there. This one was not enough. We call it like a mini explosion, but not enough that it actually knocked off the oxide. Um, so that was the first big advancement. And using this, you can do a lot of cool things. You can actually remove a trace from the IC. So for example, if you're like, hey, this transistor was driving, this trace. We don't want a bus conflict. You'd use this to cut it. And then you would also go a little bit further and you'd add this tap in. So now you can supply your own power supply, maybe bypass an on-chip regulator, or if there's a logic bug, you could potentially do that. But because this is an optical device, it's also a little bit finicky because these power levels, you have to go through this tuning process. People wanted something a little bit better. So this was, I would say, maybe not out of use, but certainly a lot less popular than it was. And there's a little demo if you want to see what this looks like, because it's kind of fun. If we can do that. So yeah, so that's like a targeting reticle. So you want to know like where the laser is going to aim.
Mm-hmm.
And then I think in a second here, you'll just see, let's see. Oh, there we go. Boom. And you see it's very instantaneous, basically. It's so quick, you don't really even see it going on. Yeah, so the modern solution is to use a focused ion beam. And this goes back to your question about, like what if you need to get a bit deeper? Well, using a focused ion beam, it's very precise. You can both remove material and you can add material. So in this on the right, for example, you saw I was just playing around. I said, hey, I'm just going to add some metal to short these two traces together, just because just messing around. That wasn't a real edit. And but there's these different chemicals here, basically, and depending on the chemical you select, some of them are etched and some of them are more deposit
I had
modes,
no
basically.
idea you can do this
Yeah.
stuff on silicon.
Oh, yeah. And then you also, because if especially if you have a nice one of these, a dual beam, it's also an electron microscope where you get, high quality images, and you can have computer controlled micro positioners that go in there and very precisely now can go to these things that you were never going to see under the optical microscope. Or even without fine needles, now you can use this to create like a larger pad that maybe you just now bring that to a more conventional probe station, depending on how fancy you're getting.
Wow. Okay, then my next question will be, before you actually probe the silicon, you have to somehow remove the packaging. So how do you do this?
That's right. Yeah. So it depends. But I would say the vast majority of people that are doing this in a production capacity are using a mix of nitric acid and sometimes sulfuric acid to remove it. So that dissolves the epoxy, and you're able to get access to the chip. Depending on the bond wire material and other things, there could be complications. So, for example, nitric acid can dissolve copper bond wires, which
Mm-hmm.
are used on a lot of modern chips if you're not careful. And depending on the chip technology. So, for example, if you have a flip chip, or especially I would say a bumper chip, where you actually have the solder balls essentially on the silicon itself instead of wire bonds,
Mm-hmm.
that can really complicate things, because now essentially where your PCB would go, to interface to this chip, now you have something in the way.
Mm-hmm.
So especially on a modern, very high density chip, it can get rather challenging to make all of this play together. And even sometimes if you can get a few connections there, then you run into issues of like, okay, well now we've taken, the heat spreader off, so it's not in a happy thermal environment,
Mm-hmm.
that it likes. And the complexity can just get out of control really quickly, depending on the test you need to
Mm-hmm.
run.
So basically, some of the chips may be super hard to probe, like because I
Yes.
don't know, you can't probe them because they are not upside down, and you don't put the wires this way, but they are just like this way, and they have some soldering points on the bottom of the silicon. They are soldered directly, so you have no access
Yes.
to these points. Mm-hmm. I understand.
That that's right, exactly. So for something like that, I haven't done enough of those to kind of understand, what the industry standard solutions for that are. But one thing, for example, you could do is you could, have a ZIF socket, something where instead of soldering it down, you put it into spring-loaded contacts,
Mm-hmm.
and that would allow you to make an edit, put it into a test fixture, maybe a little bit happier, and then, remove it from that fixture if additional edits were required, while not putting the chip through any sort of excessive soldering profiles.
Mm-hmm.
Um, because especially also once you start removing this protective oxide over the top of the chip, now there's a lot of concerns, if you get moisture into the chip, it's going to start corroding these traces, and, a lot of bad things can happen really quickly, once you take that shield off of it.
Mm-hmm. So what do you normally probe? So if you have to do this kind of thing, what is like the
Yeah.
first thing what you usually do, or what is the very often thing what you probe?
Yeah, I would say, I do a surprising number of projects where it's not, something super advanced. I think I have an example here for this micro probing. Let's see. Where basically there's just broken bond wires, and we need to just do a first level restoration. So let me see. I thought I had an example here. Okay, here we go. So, something like this chip on the left,
Mm-hmm.
I think is a good example, is I've gotten a lot of these. In this particular case, I didn't fix it with probing, but it gives you an idea of the failure. Um, where they're like, hey, we need some data off this chip. It failed in the field, because we need to help get a replacement part or something like that. Um, and maybe just temporarily, bypass the broken wire on the chip. In fact, I think I might even have, and similarly on the right, so the chip on the right is a Virtual Boy. So if you remember that old VR headset from Nintendo, and the issue that's happening on those is the bond wires are shaking off over time on these chips. So they've got kind of a little bit of a conformal code on them, but in certain units, I should say, this is not a common failure. In certain units, those bond wires are lifting off over time. And what I was doing there was I took that positioner, which you can see at my mouse
Mm-hmm.
cursor, and I just pushed it back down to show, hey, is this the failure? If we just push this back into
Is it
place,
going to work?
will exactly will it revive it? And I think it's a little bit hard to tell in this picture, but there basically were several out pixels here essentially, and you can see like this one is glowing a little less bright, and
Mm-hmm.
and that's basically because I pushed two of them together, and I was able to light up these two LEDs, but they're running at half current because there's two of them. And I was able to demonstrate, hey, this die is actually still good. I think if we just reattach these wires, we actually might be able to salvage some of these. And this is something I can share publicly, because it's just kind of a fun, side project. But I've done a lot of this for other people as well,
I didn't
similar
know
projects.
actually this can be one of the possible failures of chips, just like breaking contact with bond wires.
Yeah, this one's a bit of an extreme example, I would say, because this module physically shakes
Mm-hmm.
in operation. But there's a lot of related failures. Thermal stress.
Mm-hmm.
I've seen the bond wires kind of shear around here, relatively often. I've also seen some failures, and I don't know the exact cause, but basically the wire bonder creates kind of this profile here. And sometimes if the machine has some poor setup, it can knock the wire here. And
Mm-hmm.
if the knock is really severe, it's like basically a semi-broken wire, and after some number of thermal cycles, that actually fully snaps, and then the wire stops conducting. Um, so I wouldn't say it's super common, but it's definitely not unheard of because I've seen a lot of these failures.
Mm-hmm. And then what else you are using this probing for? Reading firmware?
Yeah. So that was that example, that we had up earlier, which was we can go, that this is an example where, I put down two needles because there was some old programmable array logic devices where some people wanted, the exact firmware out of it. And yeah, you can see a few needles here. And that was the shot we had earlier. If I don't have it on the next slide, we go back here. And that's what's going on here.
Mm-hmm.
Is it's hard to see here, but there's a security fuse right here. And this is, when I say security fuse, people use it a little bit loosely now. This is a very literal security fuse.
So these are the
It's a,
fuses which you can kind of blow up to,
yes,
and then if it's blown up, you can really read it. But if you use this kind of technique, you can connect it again.
that's right. And once again, because this is such an old chip, and it's very, signal integrity is really not that important, and yada yada. I literally put down these needles and alligator clipped the two micro positioners together, and that was enough to disable the security on the chip.
Wow. And the broken part is where the top needle is. Can you
Well, there's
move?
two needles, yeah. So
There
it's
is
a
the
little hard to
broken
see,
part.
but
Yeah. I mean,
oh,
the part which was
the
blown up
fuse,
or something.
the fuse.
Yeah.
Oh yeah, so the fuse, it's hard to see,
Yeah.
but the
That's
fuse
yeah.
was
That's what I
here.
think.
Okay, yeah, yeah. Um, I have a whole presentation that I could link if you also want to see a lot more on this project. I presented this at a Hardware I/O conference a while back. And so that was part of this, and just understanding some vintage hardware that some people in the community were really excited about.
This is interesting because this kind of technique is actually used in number of chips, and I never really thought it may be so
Well, yeah,
easy
yes
to
and
go through this.
yes and no. I mean, this is a very old chip. So a couple of things. One thing is that when people say fuses these days, they don't actually mean a fuse in the very literal sense that this is. Fuse could mean, for example, it's one-time programmable EEPROM memory that they don't have a way to reset the state on.
Mm-hmm.
And so in that case, yeah, maybe sure there's still a similar thing where you're like, there is a physical location this data is stored, but it's not in this very literal, like, oh, there's this metal chunk over here, this metal chunk, and a piece of metal that's now missing. Excuse me, that you can bridge in this very straightforward way that was done on this. Um, but yes, there are some analogs. I've also seen, for example, that a lot of these fuses on, I will just say, popular semiconductor manufacturer are actually quite large, even on modern chips.
Mm-hmm.
So even though the process technology of that chip is quite small, because of a lot of the constraints of making these fuses reliable, the fuses are quite large, and,
Mm-hmm.
and certainly the fuse macro is. So I think it is fair to say you would be surprised, even on a modern SoC, that this is still fairly accessible if you understand where the
That's
fuses
what
are
I
on the chip.
wanted to say.
Yeah.
Like I'm very surprised that if someone really would like to do this kind of debugging and they have money, then they can do
Yes.
it quite easily. Easily,
Yeah. I
easily.
the
Okay,
the
easily.
the yeah, well, easily. So the biggest constraint I would say is, we talked about, getting to the bottom layers, is that even if this laser system and the needles were able to meet the pitch of the metal traces, because they might be on the upper metal layers, which are also not as fine as the lower metal layers of a modern SoC. You still got all of those metal layers above that
Mm-hmm.
could be in the way.
Mm-hmm.
And so you still need a way to reroute those. So even though you might not, strictly speaking, require the precision of a fib, you might require its ability to reroute all the stuff in the way.
Mm-hmm. But I would be
Um,
very surprised. So these fuses, they can be also like inside of the silicon or inner layers, because I would expect something will happen during the burning process, and maybe it can damage something around it. I don't know. Yeah, I'm just
right.
guessing.
No, no. So, and this is what I was getting at, is that's why these fuse macros are relatively large,
Mm-hmm.
is because you have to have, the drivers and the sense amplifiers and, all this stuff to make this a usable unit. And then, to get the yield decent and all that, the fuse macro might be a lot larger than, the physical area of the fuse that you're expecting. Um, so yeah, it can be something that's accessible depending on the chip.
Mm-hmm. Huh. So what kind of microscope you need to have to be able to see the traces on silicon like this?
This is what I would say a pretty typical setup would look like. So this is the setup I'm using for these pictures, for example. You would typically use like these Mitutoyo, I would say is kind of like the very good brand name, microscope head up here with these long working distance objectives. I would say is kind of the hallmark of these systems. Um, Unlike a standard microscope objective where you might have to get, you know, less than a millimeter, let's say at high magnification, to a chip, these long working distance objectives, even at 100x magnification, which you might need for very fine traces, they'll still be 9 millimeters from the surface of the chip,
Mm-hmm.
which is relatively large in the scale of things. So that means, if your package, is 3 millimeters high, you need to clear the package because the die is sunk down in there, and you need to get that needle in there to
Mm-hmm.
actually access things. So it gives you room to work. So I would say that's the biggest hallmark. Plus, having this table on the outside that allows you to place these positioners and have them very mechanically stable. The other thing that may not be obvious, if unless you've played with these, is you also run into this issue about, are you moving the microscope head or are you moving the sample?
Mm-hmm.
Because especially if you're doing, say, wafer testing, you want to be able to move to a site and then move to the next site. So in that case, you're moving the sample, but not necessarily the microscope head. If you put the needles down on the chip, and you want to
Yeah, you don't
kind of
want to
pan
move
around,
the whole system.
yeah, that would end very poorly. So the machine you're looking at here is, gosh, I don't know. Let's call it a 7.5 axis machine. That lower section, essentially
So
with
you
where the
can even
probes and the
change
sample are.
angle and all the stuff.
That's right. Yeah. So certainly on a very high performance probe station, like for high speed probing, there are so many axes on those machines. Because especially what you're doing, you might have to do lots of optimization. So this is a simple machine. This is kind of like the MVP, I would say, for this type of stuff, but it goes up a lot from there.
How
Yeah.
much does it cost? I'm just curious. Approximately. You don't have
Uh,
to say exact numbers.
I think, I haven't actually priced one of these out new. So I'm not exactly sure, but I think in the ballpark of, let's say a ballpark $50,000, if that gives you an idea, which is, I think, not so bad. But that might be a non-motorized version. So I'm not sure what a motorized version would
Mm-hmm.
cost you. It might maybe north of there some amount. But certainly once you get to the high speed, highly motorized ones, well, now you're talking kind of seven figure, amounts, certainly in that order of magnitude.
Mm-hmm. I'm just curious. This is now no electronics. So did you try to watch some bacteria or something on this, just to give me an idea, like how small the silicon is comparing to this live stuff?
So what I can say as a side note to start is when I first started with this, with like, the optical microscopes and the SEM and everything, because everyone always talked about, like bacteria and viruses are everywhere or whatever, right? And it's like, I've never seen one just like in the wild, right? And so this question came up about like, where are these germs that everybody always talks about, right? And I don't know if I ever got a clear answer to that. Like, I know that a lot of the viruses and stuff are quite small, so I think you really can't see them. Certainly under the optical microscope. I think even the SEM. I'm not sure if it's enough resolution. But yeah, in theory, you should be able to see, I think, like E. coli or something, right? Because I think people put those under, microscopes. But I don't work with those enough to have like a very intuitive,
Okay.
I don't know, it
I
doesn't
was
doesn't
just
show up.
curious because I would definitely do
Yeah.
that. I remember from school, you can make like some kind of special water where you put grass or something, and then there will be
Yeah.
these bacteria, and you can actually watch them under microscope. So I was curious if you did something like this.
Yeah, I can say a few things that are kind of interesting in that regard. Is one is may not be obvious is when you use like a biological microscope, the light comes from below.
Mm-hmm.
But because chips are opaque, we
You are
can't
right.
do that. It has to come. So the light is actually injected at the top here, goes down into the sample, and then reflects back up
Mm-hmm.
for you to get your image. And so I know also this type of setup is not ideal for biological specimens. I think it basically has a resolution hit, plus issues around cover slips and all that, yada yada.
Mm-hmm.
So you might also run into some issues, even if this system had enough resolution for, semiconductor purposes, it might run into issues for a wet specimen that, has other constraints.
Mm-hmm. Okay, so what else you have on these pictures? I'm curious.
Yeah, so in this case, this was that, reading out the memory of that chip. Um, so it's a few things. So for this real setup, there is my, that's the electronics box basically, right? We've got to send signals to this to actually, run our device under test. So this, in this case, was just sending like hey, read back, the memory of this device. We've got a ribbon cable because, your stage, might not support your big original circuit board or whatnot, depending on your system. And so that was solved by putting this ribbon cable. And then you see there are some mounting screws here. They're very rigidly affixing the socket to the stage here. And you see a lot of micro positioners here, in part because for this project, I actually needed to have 3 positioners on the chip to read it out. 2 for the fuses. But what I also didn't add, and I think you see the 3 in one of these pictures I had up earlier. The reason why there are 3 in this, I think there's this funny little wire here, is because I also broke one of the pins or bond wires or something when I was decapping it.
Mm-hmm.
So there's one of these needles is bypassing the broken
Mm-hmm.
bond wire, because that was an oopsie I had on this particular chip. I've heard people, do as many as say 6 or 8 maybe positioners as individual needles. If you go above that, though, there's also specialty adapters you can get that have multiple needles per positioner, which can help you get more contacts in there. So, yeah, so that's the positioners here, objectives here. I guess one practical thing that you
Yeah.
can kind of see to the left here. Oh, yeah.
Don't
This
don't
lever.
forget what you wanted to say. So what I wanted to ask is, how do you
Oh,
know where you need to probe? I don't think there is data
sure.
sheet for for the silicon.
Yeah. So okay, so I can talk about this case study about how did I know where this fuse was.
Okay, so
Um,
first finish what you wanted to say,
oh,
and then we can talk about this.
yeah. Yeah, okay, yeah, sure. So this lever, which I don't know, I think there's a bigger picture somewhere, but
I
this
see it. Yeah.
allows you to quickly raise and lower this table. So for example, if you wanted to load in a new wafer and lift up the whole needles, move to another site, that would allow you to do that. And then when you put it down, you're at the same Z
Mm-hmm.
height that you were at before. So that's a very convenient way to do that. There's also very often these are run by a vacuum chuck to keep the sample holders in place, or even the wafer. So you can see there's a pressure gauge, vacuum gauges to make sure the system is at a healthy level there. I think one of these slides there's a picture of what these vacuum chucks typically look like. Yeah, so you can see. That's what the intended setup was. Is you have this, here's the wafer chuck,
Mm-hmm.
and it's got little holes that are probably difficult to see,
Mm-hmm.
but that allows you to put the wafer on there
Mm-hmm.
and that securely
Yeah,
in
that's true,
place.
because then otherwise, how would you hold it down? You can't really use like something to, because you could break it.
Well, yeah, I think for some systems, and I'm not that familiar with exactly when these are used. There's also electrostatic chucks,
Oh, okay.
which is I'm not that familiar with those though. I'm not sure if they're used for wafers versus other stuff, but I know that at least some semiconductor equipment for certain pieces, like masks, for example, my understanding is masks are held with electrostatic
Mm-hmm.
chucks, not with vacuum. Because a lot of these are maybe running in a vacuum chamber anyways, right? So you can't have a vacuum against a vacuum
Mm-hmm.
to get a pressure differential. So there's a few different ways to hold it down, but certainly for this, vacuum chuck is the most popular.
And these are like very special probe holders, or what?
Yeah, I mean they're very purpose built for this. You kind of see some close-ups of like some tips, for example, of what this might look like. This one is like the most basic. You just kind of shove the needle in the end, so that would just go in this hole here, and kind of stays in place. This is a little more advanced style that's got like a spring contact. So you would slide the needle kind of through an eye here that you can't see the eye,
Mm-hmm.
and that would hold that in place. And then if you need maybe like a differential probe, you might have like an actual insulator here that will allow you to have multiple connections or various things that improve the signal integrity of
Mm-hmm.
the system.
I have another question because you couple of times
Yeah.
you actually mentioned the material for the teeny tiny probes. Can we search for it because I have no idea what kind of material it is. You mentioned the English
Oh,
name, but I don't know
oh,
the.
tungsten.
Yeah, what is it?
Like,
Can you search
oh,
for
it's
on
like an
Wiki on this for this?
yeah. So it's like an element, tungsten.
Oh,
Like
Wolfram.
you'd have in a
Oh,
light.
okay, I know Wolfram.
Yeah, like you'd have in a light bulb.
Yeah, yeah, that's what I wanted to say. So it's the one which used to be used in the light bulbs.
Yes, exactly. Yeah. It's very stiff. It has very good wear properties. And it's reasonably chemically resistant. So it has a
Mm-hmm.
lot of properties that make it an excellent material for this type of application.
Mm-hmm.
Um, I don't know if you noticed for some of the probes we had up earlier, they also will have ceramic elements. Basically, if you want some better signal integrity and stuff. But I believe that even though this is ceramic, and a little more advanced, I think this area is still tungsten for the
Mm-hmm.
very end.
Okay, so now we can go back to the how do you know where to probe?
Yeah, yeah. So let's bring the other thing up as an example. So we have this guy. Um, so a little background on this project. So one of my fascinations with just these chips is just trying a lot of weird things, right? And so for this particular thing, I did what I'm going to call a weird thing. Is I have a fascination with emission microscopy. So, one of the things, I don't know if you've seen this is just mind blowing if you haven't, is if you have a very nice setup, you can actually see infrared light emitting from the transistors as they're operating. So you can actually see the flow of electricity through the chip essentially. Um, and certainly certain events can emit quite a lot of light. I don't have it handy, but for example, one thing that was an amazing demo was I programmed an EEPROM chip, and I could actually see the EEPROM cells getting programmed with a special camera.
Wow.
And I'd actually love to do more of that. It was quite exciting. So one of my questions though is, that can require a very expensive camera, especially if you actually want to see the propagation. That requires a very, very high-end system. Plus doing things like taking multiple samples and kind of averaging them, and like it's a bit of magic to actually make that work in a real system. So I was like, okay, well, what's a little more accessible? And I said, something, I bet if you just physically are blowing up this fuse, that is just going to be an enormous signal.
Mm-hmm.
That even with a very dumb camera, it might just emit like visible light because it's essentially a small explosion, and that ended up being the case. So for this, I literally basically put the chip in a dark box, turn the exposure, whatever on the camera. And I said, blow security fuse on a decapped chip, or two in this case, because there's two of them, and just boop, boop, just two little blips on the chip.
Wow.
And so I didn't have to reverse engineer anything. It just told me where it was.
How did you come
And
up with this idea?
I don't know. I just like these sort of Rube Goldberg things. And like I said, I was already looking at this sort of emission microscopy before this. And I was just thinking, what would be something cool that you could do with this? And I was actually, my original talk, which was kind of a weird, unusual talk, it was instead of reverse engineering the logic of the chip by like, lapping it down and, all this stuff, I was taking a look at the infrared emissions from the logic and saying, could we reverse engineer the chip based on the infrared
Mm-hmm.
emissions? Because then you can run a correlation analysis on the chip based on the input waveforms. And
Mm-hmm.
I'm happy to link to you that talk if you're curious. And I did it just for some very basic stuff on like, NAND NOR gates to just show that this works.
Mm-hmm.
And you can see, for example, that different transistors would turn on, depending on what you were putting into the chip.
Mm-hmm.
And
You can
I don't know,
actually run some kind of software which will stress specific parts of the chip, and you can very nicely see where these
yes.
peripherals or parts are
So
located.
yeah, exactly. So basically anywhere where there's, and this is a little bit beyond my physics background, so apologies if this comes out wrong, but my understanding is wherever there is recombination of, kind of the whole pairs, I guess, you get this emission of light, because yeah, it's going down an energy level or something. So you'll get this 1060 nanometer light coming out. So um, for a transistor switching, this is not a lot of signal. But for example, if you want something easy to see, you can put current through the ESD diodes on the chip. And I did a demo, for example, where I had a tester iterate through all the different pins of the chip, and it'll light up one ESD diode at a time on the chip, and you can kind of automatically map the GPIOs or whatever the pins to the areas on the chip. So that's a good like baby's first infrared emission project if you wanted something to cut your teeth into. And then, as the transistors get smaller, the switching times get smaller, it gets harder. So if you want to do like an analog chip, maybe with op amps and stuff, you're going to have a better time than if you're like, I'm going to get a 7 nanometer, SoC, which is it's going to be the only smallest emission that's coming out of that transistor as it switches.
Interesting. And then the infrared camera can be placed just above the optics. Optics is not going to kind of influence this like infrared light or.
Okay. Yeah, so this is a can of worms. So Toa, I will give you a high level overview and then you tell me how much information you want on this. So the quick version is that for a typical setup for this, you're doing backside analysis. So you may flip the chip over. And this works great, for example, if you have the solder bumpers we were talking about with like a chip scale package or something like that. You thin down the IC, say ballpark 100 micrometers, maybe even lower. And then what you can do is you can point a infrared camera at the backside of the chip, and which is transparent roughly to 1060 nanometer a light, and you're able to see the emissions there. So at a high level, that's what that setup would look like if that gives
So
a
with no
start.
microscope?
Oh no, that is a specialty microscope.
Okay.
Yeah. And so this whole thing will be in a dark box.
Mm-hmm.
And in the very simplest case, you just have an objective like I was showing earlier. And it's infrared rated. But it's just a long working distance objective, possibly, pointed to that specific region of the chip. But because the noise levels are so low, they do a lot of things to really extract every last photon out of the system. Instead of using a silicon, camera, you start getting to things like indium gallium arsenide InGaAs, detectors. You have to cool that InGaAs detector if you want, really good
Mm-hmm.
signal to noise ratio, because those detectors are noisy. And then, the hot new thing that I've been hearing about, and you put like anti-reflective coatings on the chip too. Um, the numerical aperture of an objective is, like how much light it can collect, and kind of determines the resolution and all this. If you have a conventional air objective, your maximum numerical aperture is something like 0.95, let's say, for a high-end objective. If you have an oil objective, you can get a little bit higher, maybe let's say 1.4 or something like that. But the cool thing you can do now is you can do something called a solid immersion lens, where you're actually just physically making contact with this chip. And now, because you don't have any air, you kind of don't have this. I don't know if the word is you're no longer diffraction limited, but because you don't have this air barrier or these other materials, it's much higher indexes of refraction on the materials, and you can get, I don't remember what, but let's say ballpark, 3 numerical
Mm-hmm.
aperture or something, I think roughly in that ballpark. And so they just layer all of these tricks to squeeze every last photon out of the system.
Are there any other methods how to find out specific places on silicon?
Of like where the current is flowing and all that.
Or where is,
Oh,
I don't
oh,
know. Oh, I guess maybe everyone knows where is memory because it's always the same, or some IP blocks probably look very similar between different chips.
oh yeah, you're asking like how would you figure out where things are on the chip,
Yeah.
you're saying if you don't. Yeah, yeah, sure, sure. So one thing of course is microprobing. I haven't done this but extensively, but one of my thoughts is, just start tapping random things on the chip and see if it looks interesting. Depending what you're doing, and can be a very valid strategy. Especially if you just want to get some high level information like, hey, is this power bus versus that power bus? Why spend all this time reverse engineering the circuitry? Just put a needle down, see what it's doing. Um, you also can, like you said, the macros can be similar. Whether that be, like, hey, I know what a flip-flop looks like, because it's going to use the same standard cells that were on another chip. Larger IP blocks, like maybe the same ADC is used. If people buy, packs of IP that they're going to have a certain footprint, and sometimes even a whole core. Like it's a little less common now, but back in the day, you would get your ARM core or whatever as a giant macro that would go on the chip, and you would route on that. Now these days, like Cortex M3, M0, for example, are they're shipped as Verilog, instead of a macro, just as an example. So you're not going to find that physical, like, oh, there's the Cortex M0
Mm-hmm.
that you used to find in the day. But yeah, there's a lot of these things you can infer if you've looked at other stuff that helps you piece it together without just going from zero on that particular chip.
Mm-hmm. What else you have on these other pictures? I'm curious.
Yeah, let's see.
Go on the
So this
top.
was
So what was the first picture?
Yeah, we can go through.
Okay.
So yeah, I was just talking. This was just talking a little bit about like why wafer test, right? For example. So briefly, I was just saying that basically you want to see if the chips are healthy, because if you start putting bad dyes into a package, that's expensive. So we're wasting material there.
Yeah, I would like to
So that's
say
that's
I was actually visiting a big PCB factory, manufacturing factory,
mhm,
and they also do. I was very surprised how many times they do optical inspection exactly for this,
mhm.
because sooner you find there is a problem, you are not going to invest money and manufacture something or continue manufacturing what is going to be bad. So I guess
Oh
that's
yeah.
very similar situation.
It is. And, there's even some trade-offs which I'm not as familiar with, but, as they're scanning across the wafer and, they find, defective chips, if there's so many defects also on a wafer, even if some chips test good, they scrap the whole
Mm-hmm.
wafer. In fact, I'm assuming that's what happened with this wafer is, it should not have this low of a yield.
Mm-hmm.
There was something wrong with this wafer, and so they said, hey, we're not even gonna try to proceed with this one. Because I think you get into these issues of everything failing later, plus all the cost to dice this wafer and sort out all the bad dyes and all of that. Yeah, so there's a lot of reasons and a lot of impetus to screen these out aggressively and early.
But I guess one of the ways how they check it is also some kind of optical inspection. They don't have to initially probe everything, or
Well, I would say the very first thing, yeah, I mean, if you see something, I would say that like, hey, okay, so an example, right? You're in the fab, which I don't know if that's the level you're talking about. I think so. Is when they put the photoresist, for example, down, right? There's a number of alignment errors that can happen for various reasons. So before they even do the etch from that photoresist, they're going to check that under various instruments. Whether that be just a simple optical microscope or maybe even a CD-SEM, depending on what the measurements they're trying to do. And if that didn't align well, they're going to strip that resist
mm-hmm.
off, and reapply it instead of trying to scrap that
Mm-hmm.
wafer. But if they, of course, just ran that etch, just blindly, then yeah, they might scrap
Mm-hmm.
a wafer they didn't have to.
Mm-hmm. That's what I thought.
Um, yeah, so there's a lot of steps there. I would say if you get beyond that, you know, alignment markers look good. You know, obviously there's no just horrific, you know, things. I would say before they even start probing, you know, the actual customer die, the fab has, you know, a lot of these test structures, you know, that they're going to use. Like this is the older way, right? So the fab's going to test these first, you know, to say like, was this wafer even reasonably made correctly?
Oh,
You
so
know, with
part of the wafer are some kind of test points where
yes,
they can probe and see if.
yes.
Oh.
Yes. And that's, you know, even if it's not a bad wafer, they're also doing things like adjusting the process parameters. So they might take some data from this and say, hey, you know, we need to whatever, bake these wafers a little bit longer because the resistance, you know, was starting to drift. And so they're going to be constantly adjusting the fab parameters based on the readings on these, on at least on a modern process.
So there can be, for
Um,
example, some kind of standard coupons, and they measure these
yes.
coupons, and then they can figure out parameters of specific layers or something like that.
Exactly. So I put like a very like simple example, right? Is you just want to see like are the contacts like meeting the resistance spec, right? No, not even a transistor, right? You know, is our metal getting put down correctly? So this is testing your metal process. If we just go, you know, top metal, go down a layer, top metal, go down a layer, is that working? Because
Mm-hmm.
because if that's not working, like don't even bother testing the rest of the chip
Mm-hmm.
because you know that's bad.
Oh, I
Yeah.
didn't know this. Ah, interesting.
Yeah, and you can see though there's a problem with this. This is the way they started doing it is, you know, you've devoted a relatively large amount of your wafer though to these test patterns and it's kind of annoying. So what they moved though on the more modern chips, I would say, is you put them in the saw lanes of the wafer because you have to separate these dies. So you see there's one die up here and another
Mm-hmm.
die down here. So it's going to saw through here and then that's sawing through those test patterns. So you don't have to waste any of the wafer to these. And similarly you can see them, you know, that's what's on all these boundaries there. And you know when you get your chip you're going to see these like part of it, like you'll maybe see, you know, because it didn't completely saw it off, you'll see fractions of them, but they're not wasted, you know, on your actual usable silicon area.
How they solve this? Because these are very close to each other, and I guess there must be no stress on the edges where they sew it. So it's like some kind of acid, or how they do it? Mechanic? No, mechanically they can't do it
Yeah,
mechanically.
it's mechanical. Yeah, I'm
Really?
trying to think. Yeah, I think I had. I don't know if I added it in here. But I had some pictures of at least. Yeah, this gives you like a good starting point. So what they're gonna do is they're gonna start by putting on this blue tack is kind of the thing, and so that's just like basically tape.
Mm-hmm.
That holds the wafer in place. They stretch it out on this so it helps release the dies when they want to get those off. And yeah, they just take a saw and it goes across and goes. They used to, if you go back a little bit, they would scribe the wafers, which is very unreliable and not very precise. So you know they would mechanically score and snap them, but you know that hasn't been done for a while. What gets really crazy though, you know, is going back. You're asking about, you know, we're talking about like usable wafer area. This works fine when you have, you know, your chips are fairly big. What about for something like an LED die that are so small that, you know, this would actually be, you know, easily 50% of your wafer, if not more. Um, so for those, they do something, and this is a little bit out of my area of expertise. They do something I think they call a stealth dicing or something like that. And this is basically laser assisted dicing, and it's crazy how it works. So um, I naively thought they take the laser and cut through the wafer
That's
to
what
do
I
this.
thought when you
That's not
say this.
it's yeah, it's not how it works. It's so they basically do is they thin the wafer. So it's you know not as thick. And then the laser is not cutting it, but it's basically I don't know what the word is, basically unannealing the wafer. So it's going in there, it's melting very locally the silicon and basically messing up the crystalline structure. Because now, if you basically give that whack, the wafer a little precise whack, it'll shatter in a very precise way along all those stress lines you've created on it. And now, because it's just a crack and not a cut, you save a lot of die area by doing that.
You know a lot about this. So what do you do?
For work, so originally I worked on, I would call embedded systems. So I started my career working on satellites, and I did that for a while, and I did find it very interesting. But semiconductor was kind of always my passion. I did a lot of side projects around it. So now I do basically two things. I run a consulting business that specializes in, basically, I would say being kind of a fixer for weird semiconductor problems. So a lot of them are around legacy systems that need support because they've lost documentation, or doing something kind of like failure analysis, where they're like, "Hey, we need someone who's more than just someone that can snap a few pictures. They can actually start putting oscilloscopes down, measure things, and tell us what went wrong with this chip. Developing code and whatever if needed." Um, and as part of this, I developed a lot of custom tools to do this analysis. And through that and other partnerships with my business partner, we also have a company now, Labsmore, that started to sell some of the tools that, at least some of the products, were originally tools that were internally used for my consulting
Do you have a
business.
website?
Uh, yeah. So we have Labsmore right here. So for example, one of our big things is making microscopy more accessible. So as part of that, we developed a line of relatively low cost computer controlled microscopes.
Mm-hmm.
So, these allow you to move around on the sample stage at something that's, more of a credit card sized purchase than kind of a, capital asset, which is traditionally the only options that were available for this sort of, machine vision systems. And we're also, putting a lot of effort into, kind of the AI and metrology and, basically making it so you don't just get a pile of images, you get some actionable data as this thing is just generating, massive amounts of data.
Mm-hmm. Hmm.
So that's kind of a growing thing, is a shift from basically a consulting to a product business, with this microscope and other specialty tools kind of in that vein.
So this microscope is 4851.
Yeah.
That's an
So
interesting number. How did you come up with this number?
my business partner, Yusuf, came up with that number, but I don't know the exact, but I can tell you that, when we talked to a lot of people about, what would be valuable, we started producing some higher end microscopes that were much more expensive. And they're great. They're wonderful systems. But the cost, is quite a lot. So what I can say is, it's a combination of the BOM cost, because we are still making these in, I would call, relatively low volume. So, it hasn't been like completely optimized to like what's called Shenzhen levels of optimizations.
Mm-hmm.
But, at the same time, we said, this has to cost less than $5,000 to be something that's accessible to people to purchase.
Mm-hmm.
For a lot of these like R&D and, light industrial manufacturing that want to inspect things. So the question was, what was the best microscope we can make that's under $5,000?
Mm-hmm.
And so that's roughly where that number comes from, if that gives you at least a starting point.
Mm-hmm.
Um,
So can you use this, for example, also for I don't know, checking PCBs if they are assembled correctly, or not only for silicon, or how this can be used? I'm just curious
yeah,
because you just explained like again, if I talk about this PCB manufacturing company, I've
yes,
seen they use these AOI machines
yes.
a lot,
So
almost everywhere.
yes. So we also have we haven't really published much about it because we've just gotten the prototype versions working, but we also have an inspection version of this microscope as well now. I'm not sure what the final price will be. It'll likely be less than the cost of this system because the optics are a little bit simpler. And that one is great for a lot of PCB stuff. So, for example, we've already done some demos of what I would call remote factory debugging, which
Mm-hmm.
could be of interest to you, where we basically put oscilloscope probes on the microscope head as it moves around, and you're able to probe the PCB. And similarly, if you wanted to do AOI type stuff, you're able to go around, take pictures, do analysis, and it's not as fast as maybe a lot of the AOI systems on the market, But if you had something low volume or R&D, you know, it's a great system for these sort of custom
Mm-hmm.
operations.
Oh, this looks interesting. Okay, let's go back to our
Yeah.
slides.
Yep.
So what else do
Sounds
you
good.
have there? All these pictures are super interesting, so I don't want to miss any of these.
Oh,
Uh, uh,
yeah, yeah. We don't have to do every single picture, and there's even maybe a few that didn't make it in here. I was saying forgot. Let's see. Yeah. Yeah, we I guess we talked about this a bit, you know, that there's you know, depending what you're doing, you know, this is more of like an impedance controlled probe. You
mhm.
know, if you're doing like RF, I don't know if this one was a differential probe or not, but you know, they also make differential probes, you know, kind of like that. I'm assuming this one is not. I think they usually have two SMAs or whatnot for that. So you know, one thing that we also didn't talk about is especially as you oops, whoa, I think I kind of made it
So
explode a
this is
bit.
your Twitter.
Uh,
If someone would like to send you a message or contact you, then this is your Twitter, correct?
Oh yeah, yeah. We should also add Twitter if you if you want to go to Twitter.
Okay,
And then
X.
just clarify. Thank you. Yeah, and yeah, and I do consulting, you know, embedded development as well, but mostly semiconductor focused these days. And certainly always up to talk about microscopes. Thank you. Um, Yeah, so I was gonna say, you know, one of the things we also glossed over is a lot of these older, I think I have a picture here. A lot of these older systems, you know, they have relatively strong transistors. So, you know, as you put this needle on there, you're adding more capacitance to the system, and you know, loading, you know, to these transistors.
Is it opening?
And
I don't see the.
oh, it's gonna switch. Yeah, I can switch now. So, oh, you
Ah,
don't see my screen at
yeah.
all?
Okay, I see it now. Yeah.
Oh, okay. Um, so at some point, you know, depending what you're doing, you might need to switch to an active probe. Especially if you're probing like a modern SoC or something, you might need a, you know, a high impedance, you know, like I don't know, follower. I don't know if that's the right circuit name, but something that just makes it so that as you're touching down onto these traces, it doesn't disturb the system, you know, to a level that just interferes with it
I was
entirely.
exactly
So
thinking about this because when I seen your probes on the EEPROM chip or what was it, and then
yeah.
so long wires going to your measurement system or something, I was thinking like, is this how reliable this can be? Like how fast signal you can run through this?
Well, yeah, and in that particular system, it was a low speed system, and I think I even had control of the clock rate.
Ah, okay.
So I was just able to clock it down. So because for me, I didn't need it to run fast. You know, the amount of time I spent fixturing it was more important than that one operation that was going to
Mm-hmm.
take, you know, a second or whatever.
Mm-hmm. Okay.
But yeah, obviously could be more of a concern for other
Mm-hmm.
systems.
So active probes are now the better way to probe this kind of.
That's right. And you know, I'm just starting to do more and more stuff with more modern chips. I have a project, for example, right now that may require me to basically fib a chip, so we can get access to some of the internal buses on that chip. And I expect for that one, which is a fairly modern, I'm just going to say sub 100 nanometer process. I wouldn't be surprised if we end up needing to put active probes on
Mm-hmm.
that. But it's only relatively recently that I've started hitting that sub 100 nanometer for actual consulting work. And so it hasn't been as much of an issue, at least up until now,
Mm-hmm.
for things I've been looking at.
Mm-hmm. Okay. What is the next picture?
Let's see. Yeah, if we go back here. Let's see. I think we showed this. Oh yeah, I guess that was so part of the progression here. Winding back,
What is this?
I had I was gonna say, yeah, so this is like, why is this called a probe card? So here is, you know, kind of a probe card installed on one of these systems. This is like old school probe card. And it's not actually quite fitting onto the system, but good enough for illustrative purposes. So here's where those needles are that we were
Mm-hmm.
looking at. And it's literally a card, and you'd have an edge connector that would stick on the end, and that would attach to your, you know, your test
Mm-hmm.
fixture, whatever driver, right? You'd have like a kind of like you'd have an ICT box if you're familiar with that type of stuff. But over time, there's very long wires here, and it has various disadvantages. So the more modern systems look a little bit closer to this. There are these kind of round, heavy-duty PCBs. This one doesn't have an actual probe in the center, so it's not the best example, but it's what I was able to find very handy. And this allows you to put actual circuitry, for example, on this probe card. So if you had a signal that needed to have like whatever, a repeater, to make it impedance controlled, whatever, you're able to do that very close to the needles that you're attaching to this chip. So you could put an FPGA on here to drive signals, whatever you need to make
So where
that test
the
run smoothly.
silicon is placed? Is it under the black?
Yeah, so this is it's not the best example. This one is, instead of being a probe card, it's actually one for testing a package chip
Okay.
that is compatible with the probe tester's system.
Okay.
Because if you develop all of these test vectors, sometimes you also want to run it on a package chip.
So this is just a standard chip tester, but a very similar way you can actually test also silicon.
That's right. But you can imagine
it would be
that
smaller.
Yeah, exactly. You have the needles and stuff there in the middle.
I'm curious, if you go back to the previous picture, how do you insert the silicon there?
How do you get to the silicon?
How do you insert this silicon under the probes?
Oh, yeah. So the way that this is supposed to be connected is this is not the right fixture for this machine. This is supposed to be up here. So this would be mechanically attached to here. And then this wafer chuck that we see here is underneath this. So the needles are mechanically supported by this level. The wafer chuck is down here. So you crank
bring it up.
Yes, that lever. Yep. So you crank that lever up. You insert the wafer in there. This slides forward. You're able to pull this whole thing, load the wafer, then you push the wafer back in, lever down, drops this bed of nails down onto your wafer.
I understand.
Yeah. And there's other schemes for more modern equipment, but they're still roughly analogous to the scheme right here. We could talk a little bit, especially if you're interested in this probe card portion, we can talk about more modern probing systems, how they're a little bit different if you wanted to do a little deeper dive on that as a follow-up.
Do you have it somewhere here in these pictures?
Yeah, it's a little further down. So we can go. I think I have. Give me a second.
We have to be quicker because I think our time is making.
We also don't have to cover everything, as long as you got your
But
full,
it's so interesting.
So this is just an example of what I would call a typical-ish. If you're testing kind of random wafers, at relatively low. This one is set up for low volume, but you can put a higher volume like auto loader on here. And this is what I'd call like a modern production prober looks like, if this gives you some context. So, and for this guy, you can even have like a wafer loader over here. It's like in a FOUP, if you're familiar with these FOUPs, these wafer cassettes. And this is going to automatically transfer it from the FOUP here onto the wafer chuck that's over here. And I think if we go down a bit, I have an example of how crazy the more modern, probe cards start looking on some of these systems. One of the things, for example, for like memory testers, which is one thing I was fortunate enough to get a tour a while back of a facility that makes memory testers, and they're really impressive because they have a lot of very big constraints. They have a huge amount of bandwidth they need to deal with, and it's a commodity, so they need to keep all of the costs on the actual chips very low. So what this means is you have the most insane tester that, in this example, I think they're testing 8 chips at the same time, versus our other system was just testing 1. And each one of those 8 sites has an insane bandwidth going through it. And so these systems, I think I don't know if I found a picture that really does it justice, but these things are beasts. Because everything is just giant data pipes, move fast. Like everything is just super optimized for ultra high throughput and performance. So I, you know, I'm not as like excited about memory as an SoC to some degree, but I really appreciate the engineering that goes into making it so we get reliable memory at a low cost, and everything that's required to make that happen is just crazy.
You know,
You
you
can
know
see
what
like,
I'm
yeah,
thinking about? Like, there must be only few engineers in the world who are really like designing these kind of systems, but everybody is
yeah.
using memories and they don't know there are these few people who made it possible.
Yeah, it's crazy too for a lot of this, because there's so many specialty parts, that go into it. I hear a lot of stories about, like whatever critical system that you've maybe heard of, that part of that supply chain, involves some specialty, whatever, that's made in somebody's garage, because it was such a little small piece of the puzzle and they found someone that was interested in working on it. And yeah, the whole supply chain to make this work, because you have CNC parts, you have multiple high-speed circuit boards, a lot of very custom mechanical interfaces. Yeah, the sheer engineering that goes into it is done by a relatively small group, especially that knows how all of this fits together, into the at the system level. I think is fair.
You are one of these people.
Uh, I I think that, I think it's one of these things though too, where I know how little I know about all of this ecosystem. So I would certainly never call myself an expert. But I think it's fair to say that I know more than some people in certain areas. But if you ask me questions about, like how do the PCBs work on this, I'm not a very good PCB designer. I can't really design, high speed signals for
But you,
beams.
you can
I'm a
probe
big fan of the
chips.
yeah, I'm a big fan of the auto router, so that's going to get some tomatoes thrown at me. So I'm going to understand pieces of this myself. I do pride myself in trying to get a good bird's eye view. But I certainly don't understand all the nitty-gritty details that's required to actually make this system
Sometimes
work.
you don't need to know all the details.
No, no, but I deal a lot with system integration, right? So like a project I did recently, right, was bringing up one of these, very expensive wafer probers. And so I didn't need to know how every piece worked, but I did need to know enough to tie it all together,
Yeah.
which is yeah,
What
can be
is the other
challenging.
pancake pan look testing system on the other
You're talking
picture?
about
The
this
other
one?
picture. No, no, no.
This?
Yeah.
Oh, no, I'm saying basically this is kind of like a conceptual idea very loosely, and this is what a physical
Ah,
implementation of
okay.
this looks like. I think this particular one might not have been an actual probe card, more like a socket like the other one, but it gives you an idea of roughly these things are beasts. Like I think part of what I also wanted to convey was just the scale. Like you can see a carrying handle here, right? So just extrapolate that to like how chunky this thing is. These things are art. In fact, I know a fellow up north of me who collects probe cards, just because he in multi-chip modules he just appreciates the engineering beauty that these things become. And I get it. It's gold wires. It's very artistic. It's very bespoke. From an engineering perspective, they certainly have a sort of beauty to them. I would say.
Okay, what is on the next
Uh,
picture? Or what do we
Yeah,
have?
so one of the things also as you move from these, manual systems, or semi-manual systems like that prober, is if you start scaling up production, you do need ways to, not just insert one wafer at a time, but actually just load up a whole stack of wafers and then, come back when it's done, right? A lot more automated. So I just had a few comments here about, what does that really look like? So back in the day, I think this was roughly, at least the first one I'm familiar with Wafers. They had the so-called Smith interface, which standard mechanical interface, I guess is what Smith stands for. And 150 millimeter, I think this is a 150 millimeter Smith pod, and then they have 200 millimeter. This was kind of the first generation, I think, of allowing the machines to kind of grab the wafer, put it in the machine, put it back. And so that was pretty cool. The thing that was kind of funny though was as the wafers kept growing, this thing, my understanding, just mechanically couldn't support them anymore because they're just getting so heavy they started flexing. And that led to to FOUPs, which I think some people maybe hear FOUPs more than Smith. Um, and so if you get like a 300 millimeter wafer, you're going to get something closer to this. And I think I told you I was lamenting about a picture I might be missing in here because I have a very interesting wafer that's in this, which is we're going to go a little bit of tangent here. Hopefully the stack doesn't grow too deep here. So that well, let's come back to it. We'll come back to it. Well, just remind me about that wafer. So this is a FOUP. So this is what's used for 300, and you see there are these fingers here, and I think that was part of the key change here. And they also maybe refine the mechanical interface here. You can see some, they've added a lot of like different locating pins and latches, and just general stuff that makes these a little bit more advanced. And it's worth mentioning there's two variations that are very closely related. There's basically a shipping configuration. So front opening shipping box is FOSB. So if you ordered a wafer from TSMC, which that's literally it's literally from TSMC, and it comes in this box. And then there's basically a more rugged version of this, which is the FOUP, the front opening unified pod. I don't know how to tell an FOSB from a FOUP. I don't know if FOSP. I don't know if there's a pronunciation there, but they're very similar. They're kind of part of the same ecosystem. Just one of them has a little more bells and whistles to actually work more reliably in a production environment.
I keep thinking about like how much money will be there when you load it with all these wafers, like 100 millions.
There's a very classic video. I don't have it handy, but where I understand the history of this video was there was some wafer loader that was having a problem. And so they set up a camera to try to help figure out. And unfortunately, what ended up happening was they had a FOUP that was basically full of wafers. And as the robot arm went to go stick the wafer in the FOUP, I shouldn't be laughing, it's not that funny. It just pushed the whole FOUP onto the floor and just shattered all the wafers. And you just see all the poor little cleanroom workers just kind of just around it, just staring at the floor, contemplating what happened, because I don't know how many dollars worth of product that was, but it was more than a couple, let's just say. And there were going to be some very stern meetings following this, I'm very sure. Yeah. I think we saw, here's something we didn't talk about. Yeah, so we didn't talk about this. So one thing I've also gotten a little bit more into recently is I don't know what you call these, electro-optical devices. And that's a whole other beast in a lot of ways. Because now, for example, imagine you want to test, an optics, port on your IC. And you also want to get it powered. So now you've got to get fibers pointed at your thing. And how do you align the fibers? And how do you make it so these fibers don't crash into the probe card? It just adds a whole other dimension to the system. So a few things that are just kind of interesting. So the first is, just how do you align these systems? And it looks, roughly something like this typically. So you have like a hexapod and you have some sort of feedback signal. So a feedback signal could be, you have your chip powered up and, like an amplifier or something is giving you like an analog out. So you can say, okay, I'm going to center this fiber by maximizing the power out. This wafer looks like it's not powered up. So, they probably have a loop back of some sort is my guess. So like maybe there's one fiber they care about for their actual test, but there'll be a second fiber that's echoing the signal back in some way just directly. So they can square, their fiber up or something like that. So, and then this can get very stressful because I got the fibers, relatively close. Without crashing. But where it gets really crazy is sometimes, and this is not something I've dealt with, I've just heard about this, is for various reasons, sometimes there are these trenches and you actually need to inject the signal from the side.
Because I've done one interview video about this, and it's because usually you may have only one layer, which is the optical layer. So you can't bring it really up or down. You have to
Yeah.
probe that specific layer.
Gotcha. And this is, oh geez, this is very stressful because you're talking about a very fragile, very expensive probe that you need to lower into a trench that has been hopefully cut correctly into your wafer. And this is very dicey. I've never done this myself. I've just heard of it. And as far as I can tell, this seems to be one of the most difficult probe operations you might do in a production setup, at least that I've heard of. Um, so hats off to people that do this and don't crash these probes, because I can see this going wrong in so many ways if you're trying to run this at any sort of scale.
Wow. Okay, go
Yeah.
through these pictures. Maybe there is also something else.
I
Maybe.
think there is, yeah, something that maybe caught my mind, but yeah, we can just scroll through quickly. I think we got most things. Yeah, the lever. We talked about this, talked about that. Wafer good. Yeah, we talked about that. The
I have never seen
optics.
this kind of pictures actually. Everything is like
Oh,
completely new for me.
oh, you're getting the fire hose. Oh, we talked about alignment. Yeah, so maybe this is a little funny anecdote here too. So, um, this, the fab is using some of these alignment markers, for as they're, doing the different layers. But also the wafer tester is going to use these as well because it wants to know, where all the dies on here. And it's going to use these to various capacities to just make sure things where they're expected and what's the, rotation of the wafer and, a bunch of stuff like that. Funny little anecdote with this, it was a project I was working on recently, this production wafer prober. They wanted to do some early validation of the wafers before they went through the full processing flow. And so a funny little issue they ran into was the alignment markers that they had planned to use in their wafer, processing. Those are on the top metal or one of the upper metal layers, and because it was an early pull out from the
Mm-hmm.
production process, we didn't have the alignment markers that we had designed the test for. So we had to kind of improvise and find some things that just happened to be on the wafer that kind of looked like the fiducials we were expecting, and I don't know.
I
Sometimes you just
exactly
got to make things
wanted to
work.
say these are like used like fiducials for I don't know PCB
Yes,
assembly, for example.
exactly.
Uh,
And I've talked to a few people about how these fiducials work, especially on the more modern ones, and it gets really crazy. I don't even think I could have a good conversation to really explain though, but it gets really crazy about what it takes, especially to align all of these in a very reliable way.
I've seen this used again when I was in the PCB manufacturing company. I've seen used these
Yeah.
fiducials to center actually the image from the AOI, so it knew
Yes.
exactly where everything is, and also scale everything properly.
Yeah. And then I don't know if you're familiar, but I believe even this original ASML logo, I believe this is a reference to their kind of their patented alignment marker. I think this they changed the logo, which some people made a little sad, but I believe the old ASML logo, yeah, I guess this is the new one. This was their alignment fiducial that was part of one of their core IPs that make their system work really well. Fun fact.
Nice.
Yeah.
Okay,
Oh
great.
yeah, this is a good one actually we didn't talk about. So especially, if you're taking these optical measurements and you want, some comparable results, same sample height, wafers, can actually vary quite a lot in height. Because you're lapping it, you get boundary conditions. Um, it's not produced the same on the edges as it is the center. It gets basically more and more uneven as you go out. So I don't know how typical, but you could see maybe these are like, micrometer deviances here from the center in this chart. It can be a lot, excuse me, depending what you're doing. So you might need to compensate that, depending on your requirements for that particular test. So there's a few different ways that you can compensate. It can be if it's a very simple, maybe you can just kind of autofocus as you're going along on those
Mm-hmm.
fiducials, and that'll give you some references. I've also seen capacitive sensors, so that's what this system is, and that's able to maintain a very good tracking as you're going across the wafer. So few different ways to compensate that and generate a map essentially as you're going.
I didn't know
And
this.
oh yeah, but it's all these sort of practical issues, and if it's simple enough, there's a lot of play in those probes. You might just be able to dead reckon it and say, hey, you know what? we can tolerate, 200 micrometers of flex across the wafer, just at a good starting position, and it doesn't matter. So I think it really depends on the particular test setup, whether this is an issue or
So
not.
basically, it could be issue like, for example, sometimes probe could be too stressed. Sometimes it would hardly touch the probes because of this uneven.
Yes, or particularly for like, these sort of fiber tests, if you're going from like, 150 to 200 micrometers above the wafer, that could significantly affect the variation of your tests
Mm-hmm.
across the wafer.
Mm-hmm.
So you might want it to be constant height, not so
Mm-hmm.
much because you can't run the test at that height, but it makes it easier to compare
Mm-hmm.
the test data.
Mm-hmm. Hmm.
Yeah.
Okay, next. We
Let's
see
see.
this
Yeah,
one.
just I guess a note here. This is there's different qualities of these micro positioners. So this would be like bottom dollar. I just want to probe some of the bond pads on the chip, and like you can
Ah,
see, it's
I,
it's
I
it's
never,
pretty.
I was, it never occurred to me that basically you need to have special positioner for the Pro because you have to move it only in very small fractions.
Yes.
I never, I was always imagining you do it by hand, and now I'm like, oh no, no, it can't be done by
No,
hand.
no, it's way too small for that. Yeah, I mean, maybe your hands are very steady,
No, no,
you
no.
haven't had your coffee today. No, yeah. Not like a PCB where you're going in there with your fingers.
So you need
So yeah,
special
this
holder, which, mhm.
yes. There's a lot of, yeah, we talked about, there's like there's the actual thing doing the XYZ motion, which is this bit. We talked about there's the tip holder, this arm that goes onto, and the actual needle itself. So there's a lot of tooling that goes into, making sure all of this is set up to actually get a working system. There's quite a few moving parts here, I would say.
Important picture. We almost missed this.
Oh yeah. So here's this really basic one. These are the ones that are my workhorse, I would say. I have a number of these, and these are good to about a micrometer-ish precision, which is fine for everything I do. I don't think my laser is even good beyond that, or at least would struggle a bit. I'm not sure the rated precision of this, but I think this is one of these nicer ones, which would maybe get you to, let's say, 100 nanometers or something like this. So you can see it's a lot heavier duty, uses these much nicer like thumb screws to turn it. But similar, like you can see, he's got the vacuum bases, to hold it down and stuff. And similarly, being more economy, this one just has a simple magnetic base. So that just, you got your steel table and it mostly stays in place. So you also see as you go up the feature set, they tend to also use more premium, even side fixturing.
Mm-hmm.
This is the one from earlier. I don't know if you wanted to take any more details, but yeah, you can see these different adjustments on here. One thing that's maybe worth mentioning is there's two z-axes on here. So this is a fine z-axis and this is a coarse
Mm-hmm.
z-axis. So to actually set this up, what I would do typically is I would start with a low magnification objective, say like a 5x or something, and that's going to have a really good depth of field. I'm going to slide this is a magnetic base because I just like the magnetic bases, but slide it over roughly into position. Use this, which is a very rough Z adjustment. It's also going to translate in X and Y because it's just a lever adjustment there. Get that very roughly in position of where I want to probe. And then this will give me a straight down Z at a
Mm-hmm.
very fine control for final touchdown.
Mm-hmm.
So you work in this kind of iterative process to get where you need to go on the chip. Yeah, good. Okay.
Good, yeah.
I think we
We
talked
talk
about
about this, yeah.
this. Yeah. I guess just maybe I mentioned, maybe not. So these are what I would use, for example, for touching down on a bond pad because they're much stiffer, much larger. And these are what I would use for touching down on an individual trace.
Mm-hmm.
You might even be able to use these for a bond pad, but it's not going to give you as good of contact, and it's going to wear out a lot quicker.
Mm-hmm.
So better to use the bigger needles whenever possible.
Are not you
Yeah,
worried you are
there's.
going to break it or something when you move it?
Oh yeah, I mean, these are essentially consumable. So for example, if you get a piece of dust on the end of the needle, it's especially for the fine one on the left. It's generally recommended just to throw it away because it's really hard to clean the tips of these.
So
And
your room is
here,
very clean?
yeah, in fact, even mine is just very basic. I run just HEPA filters in there, which at least keeps the dust level reasonably low. As kind of a compromise, even though it's not like a full clean room setup. The
Wow.
garage obviously here is just dusty. But yeah. Oh yeah, so this is just, one thing that, we're kind of glossing over is, this is very big bond pad, right? When you're touching down, it's a big target, easy to hit. And then, just bear in mind, the traces as you're going off are actually a lot smaller, but this is not what you get typically in the real world. What you get in the real world looks closer to this, where it's just all this stuff that's going this way and that way. And, it's not just hitting this, but it's also locating it in here. It can sometimes be a bit maddening. So to do this sort of work, it's at least some people are better with this. I will make very detailed diagrams of like, okay, this is where I need to touch down because it's very easy to get lost in a sea of all these traces and get, where you're trying to get to.
And then
So
someone
yeah.
will move your microscope and you will be, where I was!
Oh yeah. Well, and it's a problem too, everything has to be very vibration dampened, because you're walking around, that vibration, depending on the test you're running, can have a pretty significant result potentially. And that's why, if you remember, I mentioned, that chip socket was bolted down to the stage. That makes sure that as the probes are putting pressure on that fixture, it's not flexing. As I'm walking around, it's not walking itself, vibrating across the stage. So everything is done very consciously to keep the setup very stable.
So you can't have house close to train station or train tracks.
Well, not recommended. Or you're going to need to spend a lot of time, making it like, for example, even here, it's very common. I will just throw giant granite slabs underneath the microscopes because it just adds mass. And if you add mass, it's a very relatively inexpensive way to stabilize things. It's very common. Higher end setups will use, air cushions and stuff like that. But yeah, obviously, don't put your fab next to train tracks. You're gonna have a very bad time, I would say. Yeah. Let's see. Yeah, we talked about this, different ways to get through. Talked about that. Oh yeah, this was just another example of firmware extraction. So the key thing was here, this was a very simple like bridge this security fuse. This one was instead in collaboration with this guy Eric Tube Time. He came over and used my probe station to extract some firmware from the Sound Blaster chip, if you remember those old
Sound
chips.
card.
And so what's that?
Was it like sound card or something? Sound blast?
Yes, exactly. Yeah. Very, very popular sound card back in the day. And this was a mask ROM. And so because it's a mask ROM, there's no public documents about how to read out the data from the chip because, the fab does that, and they're not really expecting you to modify it afterwards. And after a lot of back and forth about, potential ways to read it out, there was a discovery that while we didn't know how to read out the data from the chip, we could put it into a memory test mode where it would internally cycle through all of its addresses. And I don't know if it reported a result like, hey, checksum is good or whatever. But the point is, it was looping through all of its addresses internally. And that gave this idea that, hey, if it's just going through every address, why don't we just put needles on the data bus? And if you do that, we can just read it out one bit at a time by going through all 8 signals. And I think you got like this here. Yeah, so this was like, the logic analyzer put on there, and you can see some of these strobe signals, and you synchronize that, and you have to do a little, Python code, whatever, to tie that together. But after you do that, you get the full firmware out of the chip. And that's, some of these more advanced attacks, like Chris Tarnovsky, for example, is like really known for this type of thing. He's known for like, getting these really hard, ultra secure elements, like the sort of things that would be on like a credit card or, maybe like a subway, whatever, whoever needs to protect a set TV box. But if you have enough time and patience, you reverse engineer the chip, and then you use a fib, to put down pads, probe things, put it into a test mode, and you can get it to spill its guts out. What he likes to do, for example, is we were very fortunate that this chip had just a test mode that said cycle through the memory. What this guy, Chris, likes to do is basically essentially introduce a bug into the CPU that turns every instruction into a no op. So that way, then it's just no op, no op, no op, no op, no op, and it cycles through the whole memory. And then you're able to do this.
You know what I admire on this kind of project and with these kind of people, like making so much effort without knowing if you will actually get the results.
Yes. Yes. And I think that's one thing that's important to mention. Like I mentioned, I'm doing this fib project potentially coming up. That is a very small section of people where they're like, no, we really want this data out. So a good example that is more public is, there was a some sort of big airplane crash a while back. And, basically want to get the black box, essentially, oversimplifying a bit. And one of the dies that was really critical, that had some very critical flight data, it got damaged in the crash. And like, I don't remember how much, but something like a quarter of the die was missing or something. And of course, most of the time you're like, okay, well, you're not getting the data out. But because this was such a high profile accident, they're like, all right, most of the silicon's still there. Most of the memory's still there. What do we do? And somebody reverse engineered the circuitry on that die, figured out where all the address signals were, made a PCB that filled in the missing logic, and tied that all together.
Wow.
That is probably the craziest project I'm aware of. But in that particular case, it's like, we really want to know what happened here. So like, let's do this really crazy. I don't know what the budget was for that project, but I can tell you that that was not a cheap thing to do. Just a lot of work to get to that point. But yeah, see, people can go through links, either because they're just very passionate about something, which we see a lot of stuff. Eric just loved the Sound Blaster and just wanted to kind of make that a more vibrant community. Or sometimes it's due to commercial interest, whether it be a safety investigation, or what a lot of these people were known for back in the day was piracy, basically. Set-top boxes, DirecTV, all this. There was a big kerfuffle where people were basically dumping the encryption keys out of these, so they were very financially motivated to hack these systems. Yeah. Yeah. Let's see. Yeah, we talked about this. Oh yeah, I guess one thing, just I guess one closing note for this is because this is the last slide here. I've been thinking about teaching a class at maybe Hardware IO or similar. About hands-on microprobing. I did kind of a mini version of this class. I think like a year ago, maybe 2 years. I can't remember.
Do you have a link?
I could put a link up to. I'm probably gonna spell it wrong. Hardware IO. So let's see if I can get that to come up.
Maybe someone will be interested to.
Yeah.
Learn more.
Well. Oh. Okay. Here we go. Yeah. So likely. So this is the Netherlands one coming up, but they also have a USA one that will be in, I don't know, ballpark 6 months anyways. And so that will probably be in Santa Clara, Silicon Valley area anyways, San Jose-ish. And so I'm working with the organizers. We're talking through to see if there's enough interest, if I was to develop that into a curriculum, and what people would be interested in. So like, comment, share this video, I guess, comment below.
Or they can send you some
class.
messages through Twitter or X. Or...
Exactly, yeah. So either send me a message through Twitter. Certainly I'm going to be paying attention to that a little closer. Or even if you talk to the conference organizers and say like, hey, I'm interested in if you're working with John to actually make this a class, that would be great to gauge interest if people would be interested in doing this hands-on microprobing, whether you're interested for either security reasons or you're just generally interested in semiconductor technology.
Let's see how this video will be popular. We will see.
Yeah.
Okay, we went through all the pictures. Now,
yeah, that's done.
Now the final thing.
Good. Okay, so
I have loaded a wafer onto this probe station, and we have a basic video view. You can see I can pan around. And I don't know what this wafer is, so we're going to have to play this by ear a little bit. But let's see if we can find some pads, just as a simple example. So I'm just going to pan around, and let's see. Okay, here we go. Now we're starting to get something. Great. Okay. If we could find a test structure, that'd be really cool, because then we could take a resistance measurement or something. But we can see what do we have here.
There is some text.
Yeah, the problem is the camera is so badly aligned on here right now that it's hard to read it. Maybe if we get a little bit more in the center here, or we can do higher magnification.
How do you clean
like
this?
Like
do you use air or something to clean it from dust?
Yeah, keep air. You could wash the wafer with like IPA or something, could also help. Yeah, so I should also add for our viewers, this didn't have a camera on it. I just very quickly added a camera. So it's not quite aligned right, but hopefully this is enough where we can at least run some quick tests on here.
Yeah, duct tape helps.
Yeah, this is not the intended configuration, but maybe just for illustration purposes, we'll go over here and we'll see if we can at least touch down on a few of these, which I think is a good starting point. So over here, I have some micro positioners. Let me select one that's good for this. I think here's a question for you for the camera. We'll have to figure out which side it's better to put one on. So I can do this one here, and maybe that's good. I think that's going to be the most in view of you. And so let's start fixturing this. So first thing is we have to put our probe tip holder, which I think you can see here. And I'm going to start by putting that on here. So that slots in here. Just going to loosen this. And hopefully we can push this in here. There we go. Okay. So push that in here and put the screw back in. It's a little awkward with the angle here, but give me just a second. Okay, there we go. All right. So put this in. Great. Slide that. Okay, perfect. So now we have the micro positioner with a needle holder installed, but we haven't actually installed a needle. That is the actual probe tip. And now we also, of course, can put these probe tips under the microscope if we wanted to see the differences between them. I am going to, because we want to do the bond pads, which are the large, big targets. I'm going to select the larger needles to load in here. So they come like, look, just, pack of them. You see that there?
Yes.
And I'm just going to pull one of these out. What's that?
I can see it, yeah.
And it doesn't matter as much for the wafer, but because we have very good access, but especially if we had a chip package where access was very difficult, we might bend this into a very specific shape that allowed us to get in there a little bit easier. I can do this just for demonstration purposes, although it's not
you don't
quite
need to
necessary.
bend it.
So I might use.
Okay.
You said I don't need to? It's fine.
Because you damage your probe.
It's fine. They're kind of expendable. Okay, so I bent this into kind of like an S shape, something like that. You ideally want this at a fairly sharp angle, but not necessarily exactly vertical. So I think you can see maybe there's kind of an S shape there now. And this particular holder type is spring-loaded. I'm going to start by raising up this Z height here on this knob to the maximum value to make this a little bit easier to load. And what I would normally do is move this over here, say, so that I got a little better access while loading this. So I'm going to put this here, pull this back, which does take a little bit of force. Some people, because I don't like the force on this and various reasons, you can get a different type that takes a set screw. But I just prefer the spring type. So I have it partially in. I'm just trying to get it the rest of the eyelet, but I think we also can roll. Okay, so it's past the eyelet, so it should be fairly secure in there. I'm going to rotate this now so that it's at a nice sharp angle. And now let's move over here. Now at this point, we have to be very careful because it's hard to see the very tip of this, not to brush that against anything and damage the tip. So I'm going to start moving this over here, and we're going to start getting it in position. And the very first thing is I'm going to see how much clearance we have to get it down there. There's a chance we might actually need to raise this wafer up a little bit to give us better clearance. So I may do that first. Usually I have like fixturing on here to hold the chip. So it's designed for slightly different clearance. Hold, please. Just add a little bit of height to it. And it may have worked in the other configuration, but this will just make it a little bit easier. Okay, we're gonna have to refocus the microscope now. So I'm gonna crank this up. Okay, we're starting to get back into view. Great. And I'm just going to by hand move this real quick to find some. Oh, what's that there? Is that a test structure? What is that? Little bit hard to tell. We've kind of blown out the white balance. We'll just find the standard pads maybe. So okay, that actually looks pretty good next to it. So that actually might be some test structure. So we'll stay in this area.
Okay.
And then I'm gonna move it down a little bit because this area looks nice. Yeah, so these look like test structures of some sort. Okay. And let's see if we can start getting this roughly into this position or roughly into place now. So first thing I'm going to do is I'm going to move this gross Z adjustment to get the needle below the objective. Because right now, if I moved it over, it would just crash into the objective. I'm going to rotate this needle so it's pointed away from me slightly. Just makes it a little bit easier. And start iteratively moving it just a little bit closer, a little bit closer. And I'm going to say down, 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 and just iteratively moving it closer. And I'm looking from the side. I can kind of see the needle. I have a rough idea of how close it is to the wafer. But once we start getting a little bit closer, or we have a lower meg objective, we should actually be able to start seeing the needle soon, hopefully. So I'm going to go down, down, down. I'm not going to touch the wafer, hopefully. I'm going to get very close to it because it makes the setup a little bit easier.
Because we need to see the needle in the microscope first.
Yes. That's right. And I'm also going to raise our focus a bit because it'll make it a lot easier to find that needle. In fact, we can see it. Do you see it there? In the corner?
Left, yeah, I can see.
So let me move it. Yeah, so let's actually then, I should be able to start moving it with the knobs, which I think you can see. And I didn't zero these knobs when we started, so hopefully we have enough travel range. But anyway, so yeah, okay, we got in the field view. So now let's start lowering down. So now I'm going to lower our focus down a little bit. And at the same time, I'm going to start tracking the needle down with my other hand. And that way, we just kind of track it and keep it in focus, and then keep the focal plane as well. So going down, down, moving the needle down. And as we start getting closer, then we'll be able to actually see our targets. So you can see the needle, move the focus down, and we're hopefully getting closer and closer now to be able to actually touch down.
So when you touch down, you will see how it will bend, or
Yeah.
how do you know you touched?
I can get a little more. Yeah, you'll see it bend. You know, if you were doing like a resistance check or something, you would be able to see the actual resistance measurement. We would have to set up a second needle and find like a nice test structure for that. But
this is enough.
But of course, if you can, you know, what's up?
This is enough for video. I think everyone will understand how it works.
Yeah, that's what I figured. Yeah, in fact, you can see, we can kind of see the shadow now of the needle moving, even though we can't quite see it. But let's get it a little bit closer, you know, because we want to actually start getting it on something. And I'm going to move it over here and down and down.
Yeah, you would never be able to do this by hand, I'm pretty sure. You need all these knobs.
And I'm going to, and I've made contact now.
How do you know?
A little bit further.
I see.
That's a good question.
Because the tip is not moving, but the rest of the probe is moving a little bit.
That's right. Yeah, if I just dig in, eventually it might slip if we really did force. But you definitely want to dig in a little bit to make good contact. And part of the trade-off here is you want it to be at a steep angle so it digs in really nicely. But putting it at a slight angle allows you to see it a bit easier on the microscope. So there are some compromises there, depending on what you're trying to make trade-offs. But yeah, you see, we've touched down, and if we had a couple of probes or we had some test running, we would now be able to take the other end of this, which you see I have kind of a BNC connector on. Could go on our oscilloscope or whatever our test interface is.
Thank you very much, John, for
basic
this.
demo. Let's do one bonus one if you're up for it. Let's see if we could fire the laser, because the laser is the real fun to me. But
okay.
We'll see if it works. This is not really in the right configuration for it. So I'm going to remove this microprobe.
You know what was fun about the probe? You could see the tip, but then it kind of disappeared, the rest of the probe. That was interesting.
Yes. Yeah, and it takes a little bit to get an intuitive feel for how all of these relate together. And mind you, too, in a real device, that may be very valuable, you're also going to have all these bond wires and stuff you have to navigate around. So if you move too quickly, you move in the wrong direction, you can go and wreck the chip really easily if you're not in tune with the system and all of that's going on. Okay, so I'm going to turn down our illuminator, and hopefully if I do that, let's see, I'm going to see if we can see the targeting reticle from the laser. So let me see if I can make this show up a little better.
This is so
Maybe
cool.
we just can't see it. Okay, I'm going to go higher magnification. And it might just be that it's out of the field of view and we may not be able to see it, unfortunately, because this camera is not lined up correctly. Let's see if I can push it maybe a little bit. We have the fiber here. I'm going to move this a little bit. Okay, you can barely see it there. Did you see that that square?
No.
It's kind of hard to see. Did you see that? I don't have the right adapter here, so everyth's a little you see that square there?
Oh,
that's
yeah, I
showing
see,
up
I
a
see,
little
I
bit?
see it now.
Yeah, yeah. So I'm trying to figure out if there's a way I can make that show up a little bit better. But for now, okay. Oh, that helps. Okay, let me see if that is good enough for a quick demo. Okay, so that is our targeting indicator. So that is basically an aperture that's in line with the laser system. Not an aperture, a mirror that basically says, hey, yeah, sorry, it is an aperture. It's saying that when we fire the laser, it's going to go through the same path as this targeting indicator. So I'm going to go over here and let's see if we can focus this a little better. And okay. And I can show you, I can play with that aperture size in theory. So if I do this, yep, you see I can change,
Yes.
the X direction, the Y direction. But for our demo, if I can turn this on, I'm just going to put this at maximum power and we're just going to knock a hole through the chip just because, entertainment. Do one last little focus because it looks like the focus is drifting a bit. And maybe that's good enough. Maybe it's just hard to see and it's fine. Okay, and I'm gonna do 3, 2, 1.
Oh!
And you saw like it into the chip there. Now, I did not do this in a very graceful way. For I'm saying there's multiple things that are not up to snuff here. But you get the basic idea. If you had the system set up a little bit nicer, and I can just put this on just like I said, like it's like Wrath of God. I can just go like just obliterate this chip. Now you see we've made like a crater in it. So and it'll just keep going. So like you can actually go through the whole wafer this way if you want to. Yeah, you see it's a very unhappy wafer now. You can see I'm focusing down, and we've actually milled quite a cavity at this point from the original surface up here. Anyways, so that was a very crude way to demonstrate that, but you could imagine if you set that up in a little more precise way, you can do some really interesting things with it.
Yeah, so this is best ending I ever had in my interview video.
Very good. I think that's probably a good place to call it then, unless you have anything else you want to add.
No, I would like to thank you so much, John. This was like really, really good interview. I really like it. So thank you very much for all this.
Well, thank you for hosting me, and yeah, great being on your channel.
Thank you. And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our FedDevel online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments and see you next time. Bye.